When we talk about the basis for a real vector space, you need to be aware of the concepts of linear combinations of vectors, of the span of a set, and of linear independence. So if you're not familiar with those concepts, first make sure you know what they mean, and then we can move on to talk about a basis of a vector space. So in a previous video, when we looked at the concept of span, we looked at these three vectors, v1, v2, and v3, and we showed that they span the vector space R3. So what that means is any element of R3 can be written as a linear combination of these three vectors. So for every vector B in R3, I must be able to find a K1, K2, and K3 such that K1 times 1, 2, 3 plus K2 times 0 minus 4, 1 plus K3 times 0, 3 minus 1 is equal to that vector B. So we must be able to find those K1, K2, and K3 because this vector space spans R3. Now what we want to ask ourselves is, what does a set look like? So here I've got a set, let's make set S consisting of V1, V2, and V3. What would a set look like if I can make sure that that set generates the whole of a vector space, in this case R3, some subset of R3, but what would that set look like if it can span R3, meaning like any element of R3 can be made up of linear combinations of that set. But I also want the smallest possible set. So I don't want extra elements in there that are already can be shown to be linear combinations of other elements in the set. So what would that set look like? And that is the concept of a basis. So if I define a basis, two things must hold. That basis is the smallest possible set that can generate the whole vector space. So if S is a subset of V, some vector space, then S is a basis of V if two conditions hold. Firstly, if the span of S is V, meaning if any element of V can be found by linear combinations of elements of S, but also that this set S is linearly independent. So there's no elements in S itself that can be written as linear combinations of the other. So it's that smallest possible set that can generate the whole vector space V if I use linear combinations. All right. Now, if I look at the vectors from my previous example, we've seen that these vectors, 1, 2, 3, 0, minus 4, 1, and 0, 3, 1, those three vectors span the vector space V, and you can check it again if you know how to check for span, and you should, and you can check if they're linearly independent, and they will be linearly independent. So that set forms a basis for R3. So if I look at R2 and R3, let's just start with R2. And we look at our process for looking at a basis, because we've already got all the building blocks. So if I've got a set W equal to these two vectors, V1 and V2, whatever they are, that's a subset of R2. So what I want to know is, when will W be a basis for R2? Well, there's two things. We need to check for linear independence. We need to check for span. All right. So when I check for the span, I need to look at, let B be any element of R2. And I can let B equal just X, Y. Then I need to find, so I'm checking for span now, I need to find a K1 and K2 in the real numbers such that K1 times A1, B1 plus K2 times A2, B2 gives me this XY. Now, this is a very generic example. I'm not picking values for A1, A2, B1, and B2, but I'm showing you the process we're going to follow. All right, so we're still checking for span. So I want to find those K1 and K2. So what do I want? Well, I want to look at the matrix equation generated by that. So K1A1 plus K2A2 must give me the X value, and K1B1 plus K2, B2 must give me the Y value. Now, I know there's a lot of variables here, but what our variables are K1 and K2. In this matrix equation, A1, A2, X, B1, B2, Y stands for fixed elements of real numbers. So I want to calculate the K1 and K2. So how do I know if they exist? At this moment, I don't care what they are. I just want to know they exist. Well, we saw when we looked at span that we need to look at the coefficient. We can, because the coefficient matrix is a square matrix. So let A be the coefficient matrix of this system. What would A look like? I want to look at the determinant of A because that's going to tell me something about the solution set. So the determinant of A is the determinant of the matrix A1, A2, B1, B2, whatever those numbers are. So what do I know? If the determinant of A is non-zero, then K1 and K2 exists. And I can say that W spans R2. And then if the determinant of A is equal to 0, W does not span R2. All right, but we're working towards a basis. We want to see, how do I test if this forms a basis? So we've looked at span. The next thing we need to look at linear independence. But I just want to show you what comes up. So if I let C1, C2 be any real numbers, and I consider the vector equation, C1 times vector 1, which is A1, B1, plus C2 times vector 2, which is A2, B2, equal to the 0 vector in R2. I want that to have only trivial solutions. But what does that system look like? It's going to be very familiar. C1A1 plus C2A2 is equal to 0. C1B1 plus C2B2 is equal to 0. Now here my variables in this system is C1 and C2. So yet again, my coefficient matrix is going to look exactly the same. A is going to be the same matrix. A1, B1, A2, B2. And the determinant of A is going to tell me something about linear independence. If the determinant of A is non-zero, then I know I've got only the trivial solution. And I know that W is linearly independent. I'm not writing them out because I'm out of space here. And if the determinant of A is equal to 0, then W, the system has non-trivial solutions and W is linearly dependent. All right, so we looked at the same coefficient matrix. We're testing for two different things, but if it's a square matrix, we're looking at the same thing. So what have we got here? This set W will form a basis for R2 if the determinant of this coefficient matrix is non-zero. But you have to generate the system first to get the determinant of, to know what you're taking the determinant of. So there's a bit of work in there, but that's how we're going to look at it. So it seems like we're testing for two things, but we're doing the same test. And that'll give us information about both. Similarly with R3, if I've got a set P equal to V1, V2, and V3, that's a subset of R3. This set will be a basis for R3 if the vectors span R3 and they're linearly independent. So I'm going to look, now I'm skipping a lot of steps, but you can go through the steps we did in the previous slide and see what we're looking at is the determinant of the matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. If that determinant is non-zero, then I can say that P spans R2, R3, and that P is linearly independent. And together that means that P forms a basis for R3. All right, just some examples of some standard bases. For R3, I, J, and K, we've seen what they are. Similarly for Rn. For the polynomial Pn, which is polynomials with degree less than or equal to n, the basis is formed by the following functions. For M22, or 2 by 2 matrices, here's an example of a basis of those. In the next video, we're going to look at some more concepts of basis and how they relate to the dimension of a vector space.